Okay, hello guys. In this video we're gonna pick up where we left off in the last video. In the last video you said that when you power up your microcontroller, the processor loads the startup code from the reset vector on your flash memory and starts running this code. We said that of the things that this code does, that it initializes the stack and the heap. In this video we're gonna talk about the stack and the heap and how they are actually connected together. So we're gonna start with simple ideas. I'm expecting you're familiar with the concept of stack. So having something like this is a stack, an empty stack. So you put like a piece of paper, another piece, and another. So what they call a stack is that they call a stack first in, last out. Why is that? Because you assume you can't pick anything from down there. So the last paper you put in is the first paper you can put out or take out. So putting a paper in, we call it push on the stack. Taking a paper out is called pop from the stack. That's quite simple actually. Okay. Another thing, we're gonna assume we have something like this CPU, and it have few registers. So this is SP register and something like A register, B register, C register, and actually A1 register, which is for, we're going to talk about that later. C1 and C2. So what all these registers does? So SP stands for stack pointer register. A, B, C registers are used for CPU calculations. A1 is for the return value of a function. T1 and T2 are for the arguments of function. So okay, processors usually have more than just these registers, but we're gonna assume that these are all the registers we have for now. So we actually make the explanation of the stack concept simple and straightforward. And actually the number of registers and how they work, it differs from one microcontroller to another and from one processor to another, and actually depends on the purpose of the microcontroller itself. So we're gonna assume we have simple code like this. Okay. Okay, that's a simple code, and let's take let's take all this here and place it right here. Okay, so what's gonna happen here is you actually have integer A, integer B, integer C, integer D. So you need to add integer A to integer B and place the answer in integer D. So we'll assume we have like stack pointer FF here, because as we saw up here that the stack actually starts at the higher address. So it starts from big and decreases whenever we push something in the stack. Unlike the heap that it actually increases the more we allocate variables in it. So we'll have here 5. No, we won't have 5. Okay, so yes, we'll have 5 here. And then here, and to have the answer 15, which is D, which is A plus B, which is D. Okay, so now we want to make another calculation. We want to add D plus B and add it to D. That's more or less actually quite simple. So actually we're gonna calculate B plus D and put it back in D, which will actually give us $25. That's actually quite simple, and that's actually how the processor works. Nothing unexpected. So we're gonna talk about more complex stuff that actually stack pointer and the concept of stack is totally used in. Stack is used in function calling. So when you call a function, you push the return address into the stack before you jump to the new function, because every function is saved in different location in the memory. So you don't actually want them to just go all over the place. You want to jump to a function and be able to return to where you left off. So you do that by actually pushing the return address and pushing the values of all the registers you actually changed in the new function. So if you have another function that we're gonna use the register A, B, and C, you'll need to push them on the stack before you actually change their values. So we're gonna have an example to demonstrate that in just a moment. Okay. So this is an example that we're gonna see through the stack with. So I'm gonna get our registers again. And here's our registers. Okay. So what's gonna happen here is that the stack pointer will be FF like we said. This is a hexadecimal for 1515. The maximum value for 2 digits in hexadecimal. Usually it's much more, of course, the memory is usually much more than just 16 bytes or so. Okay. So we'll have A and B, and we'll go here, and actually we'll have C here, but C will have rubbish, whatever value there is. Okay, so when we reach here, C is equal to the return value of A and of calc A and B. So we'll have stack. So first thing is that actually we push the address of the main function here, and as we said, the stack starts from the higher memory, goes to the lower, so the stack pointer will be decreased to FE. I'm assuming you're actually familiar with the hexadecimal. And we go so that we go here, we need to copy those registers into the arguments we talked about, that T1 and T2 are the arguments of functions. So we're gonna copy them here, and 5 and 10, so that they are passed as an argument for calc function. Okay, so what happens here is actually the return value of calc is the return value of my square with the arguments x, which we passed on T1, and plus y, which we passed on T2. Okay, so we will go just push calc on the stack. So calc, which is the return address of here of this line, so we can go back here, and we force the program counter to go to this function like we did here. Okay, so what happens now? Now we're in here, so we need to pass this as an argument. So actually, sorry. Okay, so we need to pass a new argument here. Rather than the x, we're gonna need to pass q. So we're actually gonna push this here. So we're gonna say T1 equals 5, and then we're gonna change this to actual still 5, and push the return value calc, and so we force the program counter here and go here. So the return value of this is q times q, which was passed on here. So what actually happens now is that we might or we might not have actually an arithmetic instruction that can use the same register twice. We'll assume we don't, so we'll need to copy this value into register A. So we'll need to push register A onto the stack. Okay, and so how far did the stack pointer go? 1, 2, 3, 4. So F, E, D, C. So I have F, 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 E, F, D, F, C, and it will be pointing to the next free location, so it's FB. Okay, so now we're gonna copy Q here. So it's also 5, but we still copy it because actually it will have to be so smart to know that it's the same value. So now we multiply Q by Q, and we'll place the answer in C, which is 25. Then we're gonna copy the value of 25 into A1, 25. Okay, so now we're ready to return. So what we do is actually pop this up so it goes back here, and it's like 5, and now we delete this and increment this by 1, so it's FC. So we want to go back to calc, so we pop this too, and we use the address we popped to jump back to here. So what does this do? So the return value, which is 25, plus the argument y, which is in T2, will be the return value. So assume we'll also make an arithmetic operation and to put the value in C, then copy it to A1. So A1 plus T2 will be 35. So to do that, we have to push C onto the stack. C equals 25. And again C will be equal to, and again the stack pointer will be equal to FC. So, and after doing the arithmetic operation, which is this, our C register will be 35. So now we'll copy this here. So it's 35. Wow. Okay. And so now we need to return again. So we actually pop C, and by doing so we actually replace C here to get it back to 25, and again increment the stack pointer to D, to being D, and we're gonna have to delete all this because it's actually popped from the stack. Okay, so what we have is that the return address of calc now is 35, and we're going back here. So we actually, before we go, we changed the argument that was passed, so we'll need to undo that, though it's not really, but it's still not smart enough to know that it's not necessary to do that. So we pop T1, and it will actually replace 5 by 5 because it's the same value, and it will pop it from the stack, and this will be FE. Now we want to go back to the main. Okay, so what's gonna happen in the main now is that we will pop the main, the address of the main function here, so we know where we left the main from. So we pop the address here, and voila, the stack is clean and empty as it was. So we go back to the main, and all we need to do is copy the argument. Just do this operation here, copy the return value of calc A and B, which we actually put on A1, and we copy it in C. And since this C is value of a function that ended, so its scope is no more, so we don't care about the value and we don't have to push it on the stack. So we just copy this here and we have 35 on C. Okay, that's easy and simple. Okay, so now we're gonna talk about the heap and its connection to the stack. So with this piece of code here, I'm assuming you have slight background on programming. So you do dynamic allocation. If you do C or actually not C, C++ or Java or C# or something like that, sometimes you use something like my class m equal new class m. So what this does is that it actually allocates a variable of type class m and returns its address or handler or whatever you like to call it back in M. Okay, so in C it's written slightly differently. You can see it here. Actually in C you do that by allocating a space in the memory, like allocating an array. So what does this do here? Actually this is a character pointer and that's the variable name, and calloc function basically returns a void pointer. I don't know actually if you're familiar with the concept of void pointer, but one of the uses of void pointer in C that it can be casted to any type of pointer you want, but it doesn't actually point to anything in the memory. So we cast it to character pointer. So now the void pointer address that was returned is now a character pointer and can point to character actually at this location in the memory. So what we're saying here is that we want 5 places of the size of a character. Character is usually, actually most of the time, is a single byte. So what we're asking here is that calloc function go and find this place for 5 characters, which are 5 bytes, and return the address of the first byte as a void pointer, and then we take that pointer and cast it to a character pointer and take its value to the heap memory variable. So how does this go actually? Okay, we're gonna talk about this in a minute. Okay, so assume we have like a heap here. A heap starts from the lower memory, so assume this is 0, 0 position. So we want to allocate 5 characters. So this is 0, 0, this is 0, 1, 0, 2, 0, 3, 0, 4, and 0, 5. Okay, so assuming we don't have anything else in the heap, what happens is that we have all this space, but only this address is returned here, the address of the first element, and we know the size of the element we took, so we can go to this to go this far, but not any further. Okay, so C is a low-level language, so this is basically a replacement for array and dynamic allocation of arrays. Or not replacement, actually they are mostly implemented this way or some similar way. Okay, so how does this actually work with the stack that we talked about? Okay, so we're gonna have this piece of code. Here. Okay. So this is actually not better. We want only this code here. Okay. Okay. So we're gonna go through this code like we did for the last two. So here the stack pointer is ff. Now we have a equals 4. So we have 4 here. Then we have this. So what does this do? Like we said, this goes to the memory and requests 5 locations of a size of character, which is a byte. So we get pointer to the first byte of 5 bytes. So we'll assume this is 0, 0. Okay, another tip about calloc that actually if it couldn't allocate, it returns a null pointer. Okay, so let's get back to our stack. So what happens now is that we go to call another function. So we actually put the main pointer here, and actually by doing all that we're doing, we're assuming that all the addresses are actually on byte, which is actually usually not true, but this is to make things easier, to not go for calculating the addresses. It takes two pieces of the stack or 4 pieces of the stack depending on your memory size. We're not gonna go this deep in this video. Okay, so now we go here. So we need to change A and B to place X and Y. So what's this gonna do is that we go here, push A equals 4 and heap memory equals 0, 0. Then we just subtract this by 2, which is C. C. Okay, so now we go just delete this and delete this, and we're gonna load our new values. So here is x equal 3, which is this, and y equal x plus 5, which will make this equal to 8. Okay, so now this function ends and it needs to return here. So to return here, we need to pop all the variables we actually pushed. So when the main comes back, it becomes the way it just left. Nothing changed in its registers. So we go here and delete those and pop those one by one. So we have this goes back here 0 0, which is our heap memory pointer. So we delete this. Then we pop back A, which is this here. Okay, so after we returned all the registers, we add the 2 we subtracted from the stack pointer, so it's E. Now last thing we need to do is pop the address of the main to know where we should go back, and voila. So we're back in the main, and this is actually how it goes between the heap and the stack. What actually happens is that when we were here, we had okay, actually you can just remove all this because you don't need it anymore. So you actually can have the code and still look at it. Okay, so we had a stack and the heap. This stack heap. So at some place here in the stack, we had a pointer that pointed actually to a place in the heap which got 5 places. So this is actually how the connection between the stack and the heap works. You dynamically allocate some space in the heap and take a pointer. Actually it's usually pointer the first place in this series, and this pointer, when it's used locally, it's pushed onto the stack. So you don't push all your heap or the dynamically allocated array, because it may be so large array, maybe 100 elements or 500 elements. You just push a pointer to the first one into the stack, and when it's when the function ends, it's popped and thrown away because its scope is over. So last thing we can talk about the stack and the heap. You can easily run out of heap, and there is something called memory leaks, where you actually allocate some space on the heap and then make the pointer that's pointing to the first one in the first element of it, point to something else. So the space that you actually allocated is no longer accessible. We can make a separate video about the memory leaks and what causes them. Another thing we can talk about is Stack Overflow, if you actually heard about Stack Overflow. Stack Overflow, back in the past the memory was so little, so actually Stack Overflow is something that is not unlikely, it was likely because you didn't have much memory. So the things you were working with couldn't actually fit in your memory or on your stack, especially if you initialized a small stack. Another thing actually that goes nowadays, when we have memories in gigabytes on computers and microcontrollers, we have sometimes few megabytes. So how can you run out of stack? Actually, if you make a recursive call, if you know what is a recursive call, you can also make a separate video about that. But if you make a recursive call that runs to infinity, like you make an infinite loop, so basically like you saw, you'll keep pushing the addresses every time the function calls itself. It will push the address of the last function again and again and again and again, and push even the registers if there are registers that changes, so you can run out of stack quickly. Another thing that can make you actually run out of stack is that if your system have so many interrupts. If you're familiar with the interrupt concept, maybe you can also do a video about interrupts. But if you're familiar with interrupt concept, your computer works with interrupts all the time. When you do a mouse click, a keyboard, you press a button on your keyboard, anything you do drives an interrupt that needs actually to be handled. So the interrupt handler are usually functions, and so calling them to handle the interrupt needs the function that was actually working right now to be pushed onto the stack, the way we saw. So if you have so many interrupts or something went wrong on your system, causing so many interrupts to happen, this may actually cause you also a stack overflow, which is actually not likely on a PC computer, because the memory is so large and the operating system tries in some ways to handle the interrupts and make them not cause a stack overflow. But in the embedded systems, you absolutely have to take care of that and make sure you don't put everything on interrupt, and make sure that your interrupt service routine or interrupt handler is as small as possible, so it don't cause stack overflow. I like to mention just Stack Overflow because it's a famous website for developers, and it's good to know where that word came from. Thank you for watching, and if you like this video, please leave a like and subscribe to our channel. And if you have any questions or special requests for videos, please leave a comment. Thank you.